Now let's do part B. Determine whether carbocation is stabilized by an adjacent chloro group, a chlorine attached directly to carbocation. Justify your choice by drawing resonance structures for the carbocation. Okay, so the answer to this part B and C will be yes or no. I'll first draw our structure as okay, we have phenyl here. Okay, that's that aromatic ring you see. And assuming, okay, we are only concerned with the chlorides, so imagine we have one chloride here, which is gonna act as a leaving group, and then two hydrogen attached. Okay, now when he leaves, okay, we are in SN1 reactions in which the leaving group leaves first. When he leaves, okay, let me actually, yeah. It's bad. Okay. It's gonna have sp2 hybridized carbon, so we need to spread them as far as possible based on the Vesper theory that you learn in general chemistry. So we need to have the 120 degrees angle, and then we have a carbocation here. Okay, and we're gonna compare this with another that has the adjacent chloro group to the carbocation. So I'm not gonna draw all of this. It's fundamentally it's the same thing. So I'm just gonna draw several carbocation structure that has more halide group. Here is one, and we can have 3 chloride attached in the carbon, this alpha carbon there. So in other words, since chloride was initially over there, let's actually check our hydrolysis data. So we have HHCl, that's like a 0.22, and the HCl 2.21 is pretty much across the row, and then we have finally 31.1. As you see, the rate is increasing as we put more alkyl, the chloride, to the carbocation. So this confirms, or this can answer our part B, that yes, it's stabilized by having the adjacent chloro group. So the answer to that is yes. And justify your choice by drawing the resonance structure for the carbocation. We can do that by first drawing the lone pairs around the chlorine. So I'm going to choose a middle structure. The lone pair you see can actually form a double bond between the carbon and chlorine, or pi bond, and our plus charge from the carbon will now be distributed to the electronegative chlorine atom. Okay, this has to be the resonance arrow with a bracket. Okay, since we have a stabilizing factor, and then we will have more arrows when we have this, it shows that the having more chloro group is stabilizing. So that answers part B, and part C, determine whether a carbocation is stabilized by an adjacent bromo group. Justify your choice by drawing resonance structures for the carbocation. It's the same question, and except that we don't have the HHBr, just like we had 3 structures to compare earlier. We can only compare the 2 bromide and 3 bromide. So my point is, here we have bromide, bromide H. So that and Br, that. Comparing the data, obviously, the having 3 bromo, having more adjacent bromo group to the carbocation is stabilizing factor. Therefore, this answer is also yes. And I can draw now the 3 bromo attached to back up my answer. So let me draw the carbocation with a bromo, bromo, and the phenyl at the bottom, plus charge. There's a lone pair, which is gonna act importantly in the resonance structure. I can move the lone pair from here to over there to form a double bond. Then my plus charge from the carbon is now spread to the bromine on the left. But also, I can draw another arrow from the right side here, the lone pair, to form a double bond on that. And oh, I forgot second arrow that actually pushes this double bond arrow to the left side bromine. Okay, remember the carbon cannot have 5 pairs of electrons. So this is what we have. See, we have more what? More resonance, right? 1, 2, 3 versus 1, 2. Therefore, I just confirm that the carbocation is stabilized by an adjacent bromo group.